Imagine two protons floating in the deepest, darkest void of space, completely separated. If one moves, the other reacts, but how? They aren't touching and there are no strings attached. It's easy to think they communicate instantly like magic, but physics doesn't allow magic. It requires a mechanism. The answer is that space isn't empty. It's a fabric that can be disturbed, and we call that disturbance the electric field. Think of the electric field not as an object, but as a property of space itself, a set of instructions at every point. It's exactly like a wind map. The wind exists even if there's no leaf blowing in it to prove it. The intensity of the field is just the wind speed, stronger near the source and weaker as you move away. Mathematically, we define this intensity as the force a tiny test charge would feel, divided by that charge's magnitude. To calculate this precisely, let's place our source charge at the origin and pick a target point in 3D space. First, we find the position vector, let's call it r, which points straight from the source to our target. The field strength depends on the inverse square of the distance, so we divide by the magnitude of r squared. Then we multiply by the unit vector to lock in the direction, giving us the full Cartesian recipe for the field. Now pause and predict. If we drop a second source charge nearby, do the two fields collide and crash? They don't crash, they stack perfectly on top of each other, a rule we call the superposition principle. You simply calculate the vector for charge 1, the vector for charge 2, and add them up to get the total field. Finally, to find the force on a real particle, we just multiply our field vector E by the particle's own charge, Q. But watch out, if that particle has a negative charge, it flips the vector, swimming exactly opposite to the field's flow. The electric field is just a map of potential force waiting to happen. Use the field to describe the space and the force to describe the push.